Hi there. Today we're going to be talking about Lewis structures. Specifically, this is a review of lecture 13 on Lewis structures. I'm going to go ahead and share my screen here so that we can get moving forward. Here we go. So Lewis structures. Specifically, what Lewis structures are and why we need them. So Lewis structures break down the structure and bonding of different molecules when we put them together. Basically, Lewis structures are the backbone, I would say, of the simple understanding of chemistry. It's kind of like, when in kindergarten you have the numbers are learned, and then first and second grade you have addition, subtraction, or basic addition, subtraction in kindergarten. This is kind of like your basic structure and bonding of different molecules that we're going to build upon this concept throughout chemistry and all different types of chemistry. And it explains basically everything, why different polar and nonpolar molecules aren't going to mix, or why polar and polar will mix and nonpolar will mix, is determined in part by the Lewis structures and how the different molecules interact with them. I mean, Lewis structures don't determine those, but they give us the basic understanding to be able to move forward to other concepts, which will explain that. So at this point in class, everyone should have a basic understanding of molecular geometry, molecular orbitals, and the different things. But going back to Lewis structures is important, because if the base foundation of understanding Lewis structures isn't there, it's going to make it harder to understand and predict what the shape of the molecules look like. There's two basic things we need to pay attention to when we're making Lewis structures, and that is the lone pairs and the bonding electrons that come with each element in the periodic table. When we're trying to understand Lewis structures, it is very, very important to understand that the Lewis structure is essentially a way of drawing molecules with a dot representing each valence electron. So every time you see a dot, to start out with, it's going to mean one valence electron. Lewis structures love symmetry. So when there's going to be a big complex Lewis structure, there's going to be some element of symmetry to it. Meaning that I'm going to demonstrate just a little bit later, but I'll go into that. Just something, a key point to remember, that they love to be symmetrical. So moving on, here is our good old friend periodic table. For Lewis structure, you need to know the valence electron of each element. On the test, you're always going to have a periodic table. So as long as you know how to read the periodic table, you won't have to memorize any of those, which would be impossible. I mean, technically possible, but it'd be really hard. But if you remember that you have your different groups going across the top, and the group number, or specifically where it's at on the periodic table, is going to correspond to its valence electron. So in our group 1, we're going to have 1 valence electron. Group 2 is going to have 2. We're going to skip the transition metals and go over here to group 13, which is going to have 3, 4, 5, 6, 7, and 8. And these are the number of electrons that are going to be represented in our Lewis structure. So if I asked you, okay, how many Lewis structure dots would be in an element like nitrogen, it would be 5, because we have 5 valence electrons. Moving forward, just to get a little bit of an example. So we just did the refresh reading. So there's going to be the valence electrons from everything. It depends on which group it's going to be in. Drawing 1 dot for each valence electron. So we're going to do an example with oxygen. So oxygen, if we would go back to that valence electron, is going to be in that, it's going to be in that 6 valence electron group over here on the right. Let me just go back so I can show you. Oxygen is going to be right here, group 16, but it only has 6 valence electrons. So then we go back down to our example. We draw it. It's written out as helium, because helium is going to be a full valence electron shell. But then we're going to have a 2s2, 2p6 right here, which means that together, that would be the full representation of oxygen, which when we draw it out, I believe I had us, yeah. So I'm going to draw it out for you real quick. Right here, we're going to have oxygen. So when we're drawing our Lewis structures, we're going to want to go in a circle, drawing them around whatever element is. We've already determined the oxygen is going to have 6 valence electrons. So we're going to start right here. I'm going to go 1, 2, 3, 4, 5. That was a bad one. I wish I would have put that a little bit over, but it's kind of hard to draw with the mouse sometimes. 6. So then we have 2. Let me get my eraser real quick. I'll straighten this up. So then we're going to have, I did not mean to draw a line. I want to draw it with a, all right. Sorry for the technical difficulties. But if our professors can have technical difficulties sometimes, then I guess it's okay for me doing this for the first time to have a little bit of technical difficulties. So here we go. Oxygen has 6 valence electrons. We started them by drawing in a circle. So we went 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So we have our 6 valence electrons around oxygen. Now it's important to note that oxygen is going to have, I think I have to exit this. Okay, I actually move forward in the PowerPoint. So when we are reading our bonding electrons, we look at the Lewis structure that we just drew. We looked at the periodic table. We said, okay, oxygen has 6, and we drew it out on this. But the bonding electrons can be read from the periodic table as well. So we look right here. There's 2 dots around our element that do not have a partner, that are not connected. This is considered a lone pair. So that means that oxygen is going to want to naturally form 2 bonds with something else because it has 2 little guys that want a partner. Like everyone doesn't want to be single. They want to have a little partner. They want to be in a relationship. This can also be determined from the periodic table. So remember that number, oxygen has 2, like it wants to have 2 little buddies. So if we go back to our periodic table right here, oxygen is 1, 2 away from being a noble gas. So it means it wants to have 2 more added to it. It wants to have 2 bonds formed with it. Nitrogen is going to be 1, 2, 3 away. So it's going to want to have 3. Carbon has 4 valence electrons, and they're all single because remember we draw out carbon. It's going to be just your normal. Let me go back to that. Carbon is going to be your normal carbon, but it's going to have 1, 2, 3, 4. And since none of those are bonded to something else, then all of those are going to want to get a mate. Everyone wants to have someone they're going to be with. They want to have a husband or wife. So 1, 2, 3, 4. Those are 4 bonding electrons that we can get from carbon. From boron, it's a little bit of an exception to the rule that's covered later in one of the later lectures. Boron is going to want to have 3, and it's going to be the only one of the elements that actually only forms a perfect octet of 8. An octet is when something has 8 valence electrons, like your perfect, quote, quote, normal noble gases over here on the far right. So if we come back over here and I ask you, okay, so how many bonding electrons are going to be in lithium? Lithium has 1 valence electron. And when it's on this side, it wants to lose it to get to 8, because that's an easier way for it to get to become a perfect normal gas. So it's going to have 1 valence electron that it wants to get rid of. So it wants to bond with one thing. Beryllium is going to have 2. Magnesium is going to have 2. Sodium is going to have 2 bonding electrons, meaning that they're going to want to form. Magnesium is going to have 2, sodium is going to have 1. meaning that they're going to want to form two bonds or something. So magnesium is probably going to form two bonds. So like magnesium was going to bond with oxygen. Then we would have an oxygen. Let me just do a little, that's actually not a good example. Let me go back down to where I was on my PowerPoint slide. So we have our bonding electrons, which can be read from the periodic table. Periodic table is super simple to skip through some of the basic steps. If you go back to Dr. Mortensen's slide, he has a lot of tricks for drawing out Lewis structures. There's actually, I think it's called a comprehensive breakdown or something like that, where he tells you step by step the perfect way to do it. But in the end, you can do it just by, I need to erase that real quick. One sec. So I'm going to go to annotate and erase this. So we just drew oxygen, right? So now let's draw oxygen gas. So if we had two oxygens, what is that telling us as far as our valence electrons? Okay, so we're going to have two that are going to want to be bonded from the first oxygen and two that are going to want to be bonded from the second oxygen. But each oxygen is going to have here again 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4. Sorry, those are not perfect circles. 5, 6. So when we look at these, we say, okay, 1, 2, and 1, 2. These ones want to form bonds. Everything wants to be to a perfect octet. So what's really going to happen is that this one is going to pair up with this one, and this one's going to pair up with this one. Because they're bonding with each other, it's going to rewrite the way that we actually draw the Lewis structure. So I know I told you to go in a circle, but in all reality, it would look more like 1, 2, 3, 4, and then the single bonding electrons, one would be right here, one would be right here. They're actually going to be right here and right here. And then same thing right here. We have one lone pair right here, one lone pair right here. And then those single bonding electrons are going to be right here. And they're going to form a bond with these, that was a poorly drawn bond, but the top valence electron is going to bond with that one, bottom is going to bond with that one. So anytime that you see a line like this, it means that there are two electrons in that line. So how many electrons do we have just right here in our little molecule? We have 1, 2 lines. So it's going to be 2 lines times 2 electrons per line. So we have 4 electrons that are right there. They're kind of shared between the two oxygens. So then a way to check and know that this is correct is going to be by determining the bond order. So our bond order is going to be equal to the number of needed electrons minus the actual electrons divided by 2. So if this oxygen wants to be a perfect molecule and wants to have a full valence electron shell, it's going to need 8 electrons. This one as well is going to need 8. So there's going to be 16 needed electrons. Well, how many valence electrons does oxygen actually have? Well, we already determined from the periodic table that oxygen is going to have 6. The other oxygen is going to have 6. So it's going to have 12. Okay. And then, just like I said, like our equation was, we're going to subtract it. So we're going to get 4 right here. It's going to be 4 on top equals 4. 4 divided by 2 is 2. So our bond order is going to equal to 2. Bond order. And then when we look right here, we have 1, 2 bonds. Okay, so that checks. That's going to be covered right here in, let's clear everything. Right in the next slide. So back to bond length and strength. So we just determined that if we went back to our example, O2 is going to have 2 bonds, okay? Well, what if something only had 1 bond? So you had oxygen bonded, or it's not a good example. What if we went back to our periodic table and we had 1 hydrogen bonded to a fluorine? So we're going to have 1 valence electron that's available, because you're going to have 1, 2, 3, 4, 5, 6, 7. So there's one empty dot. Hydrogen's going to have one. They're going to bond, and it's just going to be form one bond. So moving forward to where we were talking about bond order, bond order and how that relates to strength and length. One is going to depend on the bond order. So oxygen 2, or oxygen gas, is going to have a bond order of 2. So the different bond orders that we can have are, oops, did not mean to click. We can have a 1, a bond order of 2, and a bond order of 3 for simplicity. Later, in other sections, you're going to learn there actually can be decimals or fractions of bond orders. But for now, just think of it as 1, 2, and 3. And easy way to remember this, as far as strength and length goes, think of it as a 1. So you have one person by himself. He can, he's just by himself. It's pretty easy to move one person. If someone's going to tackle him, he could pretty easily just tackle that one person. But then when you have a couple, they're going to want to hold hands. So there's going to be 2 of them. They're holding hands together. It's pretty difficult to break apart holding hands versus just one person. So you have a couple that's holding hands. So imagine like the guy holding the girl's right hand and his left hand, so like facing each other. You can even use a couple. So like one couple that's just walking, holding hands. This is better. I thought it out in my mind, but then I forgot it. So one couple that's holding hands, walking, okay? And if you're coming and you're running through like Red Rover, it's pretty easy to break that bond. But then when they're holding hands facing each other, you have to break through 2 hand bonds. So that's a little bit harder. And then when they're 3, they're giving each other a hug. And trying to break someone apart when they're hugging, especially when they're a couple, that's just going to be really, really hard to bust through all 3 of those. So the higher bond order means that they're going to have more strength, and they're going to be closer together, meaning that they're shorter and they're going to have more strength. When they're walking side by side, holding hands, they're a little further apart. When they're facing each other holding hands, they're going to be pretty close. These ones are going to be a little bit shorter, and these ones are going to be the shortest. So in all reality, it should have been drawn like 1 bond looks like that, 2 bonds is going to look kind of like this, and 3 bonds is going to look like this. So longest is going to be a single bond, double bond is going to be a little bit shorter, and triple bond is going to be the shortest. The triple bond is the hardest to break apart. When you're thinking about size of the atoms, the size also plays a role. Bigger atoms are naturally going to have more and more layers of electrons around them, so they can't actually get as close together. So if you had a huge atom that was bonded to another big atom and they only had a single bond between them, but then you had, our hydrogen and fluorine bonded to each other, the hydrogen and fluorine are going to be so much harder to break apart because they're so much smaller molecules than 2 huge, massive atoms from lower in the periodic table. So just remember, between bond order and strength, that it depends. The bond length and strength comes from the bond order. And if you just remember that simple couple analogy, you should be pretty good to go as far as exams. Okay, so Lewis structure 105, you have like Lewis structure 101. Because we're in 105, I put 105. Knowing how to draw Lewis structures, the basic things you want to remember when you're trying to draw them is you want to double check them using the number of valence electrons, the octet rule, and the formal charge. So if we went back to our periodic table, we all know that elements can be in other different charges. For example, if we had a magnesium, and magnesium is going to want to be naturally found as 2+, that would still be magnesium 2+ is how we would draw the Lewis structure for it. So it would just look like, magnesium 2+ plus would be, and what's this actually saying? Well, the formal charge of magnesium in this example, say they'd ask, okay, what is the Lewis structure of magnesium 2 plus? Well, then the answer would just be, you have magnesium 2 plus. That's your answer. Because magnesium 2 plus is saying that there is 2 less electrons in that atom, and that's going to be my Lewis structure. Say I had oxygen 2 minus. Well, an oxygen 2 minus is going to have 2 extra electrons. So it's already going to have 8 valence electrons. So just pay attention to your formal charges when you are drawing your different valence electrons on each atom through the different structure, because if we pay attention to the formal charge of each individual atom, but also as of the molecule as a whole, is going to help us when we're trying to determine the Lewis structures and if it's correct. So the number of valence electrons was essentially what I was doing earlier. I kind of went out of order here, I'm sorry about that. But essentially the number of valence electrons is like my oxygen is going to come with 6. For the number of needed valence electrons would have been 16, because each oxygen is going to want to have, a perfect 8. So that's where I went through, I determined the bond order. And because I found the bond order, I knew, I'm going to have 2 bonds formed between oxygen gas. So by double checking, by looking at the number of valence electrons, you can make sure you're getting that right. And the octet rule is just what I was saying earlier as well, is where one atom is going to want to have 8 valence electrons. Like everything in life, there's going to be exceptions. Not necessarily always. Hydrogen only wants to have 2, but for the most part, the octet rule stands for everything, and you need to remember that as you're drawing your different Lewis structures. So let's go ahead and do just this quick last practice problem looking at this, and let's double check to make sure that this is correct, okay? So I have methane, which is going to be 2 carbons and 6 hydrogens. Well, if I go back to my periodic table, I have carbon, which is going to have 4 valence electrons bonding with 4 valence electrons, and there's 2 carbons, so there's going to be 2 of them, right? And then I have hydrogen, which is going to come with just hydrogen is going to come with only 1 valence electron, but there's 6 of them. So 1 times 6 means that I'm going to have 8 plus 6. So I'm going to have 14. I did my math right there. Yes. Okay. So I'm going to have 14 electrons. That's my actual number of electrons. Okay. What's my number of needed electrons? Well, carbon is going to have 4, but it wants to have 8. So it needs 4 more. The other carbon needs 4 more as well. So there's going to be 16 needed electrons right there. And hydrogen, like I just said a few minutes ago, hydrogen only wants to have an octet of 2. It's the one thing you just need to remember about hydrogen. So these 6 hydrogens are only going to want 12. So they're going to want 12 right here. And these guys are going to want 16. So then if I add that up, I'm going to have 28. That was a terrible 8, but it worked. Minus 14. So I'm going to get 14 valence electrons. And then if you remember the formula, think back to it. I need to divide that by 2. So if I divide that by 2, I'm going to get 7 bonds, sending bonds that are going to be formed. And I go over here and count. I have 1, 2, 3, 4, 5, 6, 7. So that looks like it would be successful. And if I was drawing this out as far as like Lewis dots would go, then I'd have my 2 carbons. Carbons are going to be in the middle because they are the most common thing you're going to bond with. Carbons are like always in the center of your Lewis structure. But I'd go around, I'd put all my dots like this. And then I'd have my hydrogens, and then I would go around connecting them, just drawing them on like this. And everything is going to bond. And what that is essentially saying is by checking the octet of each Lewis structure that I'm drawing, by checking the octet rule, I'm saying, okay, is there a formal charge around my carbon here? My carbon came with 4 valence electrons. So it came with 1, 2, 3, 4, but it's sharing this one with hydrogen. So it has 1, 2, 3, 4, 5, 6, 7, 8. So this carbon has a formal charge of 0, and it fills its octet rule. This hydrogen has 1, 2. It's good. That one's good as well. That one's good. And this other one's going to be bonded to my remaining 1, 2, 3. So by checking those simple things that I said in the slide before, the number of valence electrons, the octet rule, and the formal charge around each element that is coming into our structures, we'll be able to make sure that we're drawing the right Lewis structures. So recommended path for success in this class when it comes to studying Lewis structures is know how to draw them. They're important. When we understand the interaction of molecular bonding is going to be important later. But when we understand the interaction of molecules, we understand chemistry, because chemistry is, when you think of chemistry, you think of explosions and stuff. Well, understanding what's going on the molecular level is going to help us understand why things are exploding. And Lewis structures are just the first step, kind of like that elementary math of why chemistry happens and why chemistry does what it does. If you haven't already done so, I'd recommend memorizing the polyatomic ions by practicing drawing their Lewis structures, because it's a good way to understand how they're all going to be connected. And it's just a good practice of drawing Lewis structures in general. So if you have any questions, talk to Dr. Mortensen or one of the TAs. They'll be able to help you. But that is a great way to get better at understanding polyatomic ions and doing better at Lewis structures in general. So good luck, everyone. Hope that helped a little bit. Sorry if I stumbled over a few things, but good luck studying for the tests.